Question 5. Now this question, there was no mark scheme and all the students were awarded the full 4 marks because of a typographical error. However, let's attempt it. I think maybe the typographical error is at -EA. Doesn't really look like a divide, I'm not sure. But we're going to attempt it and hopefully get the correct answer, but obviously I'm not fully sure if it's correct or not because there's no mark scheme for this. However, once I work this out, I'll be pretty confident, and then obviously I'll ask my teacher as well to check it if I decide I want to. So first things first, if we're trying to find A, well, first things first, with any type of unhomogeneous constant question, especially more than 2 marks, we need to find a natural log. So ln k equals ln a minus ea over rt. What are we trying to find? We're trying to find a, so we get ln second part, ln a equals ln k plus ea over rt. ln a, now let's substitute the values in. ln k, well, k is at 3.46 times by 10 to the power minus 8 units s to the power minus 1 plus EA, which is activation energy. And activation energy in this case is given in kilojoules. However, look at this, the gas constant is given in joules, the activation energy is given in kilojoules. Well, we need to convert activation energy in joules then, so it matches the gas constant R in joules. So we're going to times by 1000, we get 96,200 joules per mole to the power minus 1. So joules, so that's a bit sneaky, the idea. We need to time by 1000 to get convert into joules because the gas constant is in joules. Once we do that, we get 96,200 over R, which is 8.31 joules. 8.31 joules times by the temperature, which we need in Kelvin. So if it's 25 degrees Celsius, we need to add 273, which will give us 298 Kelvin times by 298. So fourth thing, what do we get at ln A as? 3.46 times by 10 to the power minus 8 plus 96,200 divided by 8.31 times by 298. We get, let's just double check, 273 plus 25 is 298. 892, yeah, it's 298 Kelvin. So we get ln A equals 38.84702674. That's all the digits I've wrote on my calculator. But we're trying to find A, so what we have to do now is therefore A equals inverse of this, which is e to the power 38.84702674. The same way we took the natural logs to get rid of this e, the same way we're going to add to get rid of the natural logs, we're going to use e. So yeah, it gets a bit complicated, but the whole point of taking natural logs was to get rid of e, and now the whole point of doing e is to get rid of natural logs. And therefore we get A equals shift E on your calculator, that button, to the power of my answer, and I get so we get so get 3 ln k. Oh my days. I made a massive mistake, which is actually really good because you guys can maybe learn from my mistake, but I'm definitely learning from my mistake. It's ln k, so we need to do ln of the value of k. Okay, so silly mistake. So ln of k, which is 3.46 times by 10 to the power minus a, plus 96,200. Want it in joules because activation energy is in kilojoules. We want it in joules because the gas constant is also in joules. Divided by 8.31 times by 298. We get natural A ln A equals 21.66761455. Therefore, raised to the power of E, we get A equals E to the power of this. So A is equal to E to the power of my answer, and I get A equals a ridiculously large number. But I'm going to put it in standard form, 2.57 times by 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9. 2.57 times by 10 to the power 9. And the units, well, if we look at k, k is to the power s to the power minus 1. So if k units is s to the power minus 1, that's a first order reaction. First order reactions, k has units of s to the power minus 1. Therefore, a will also have units of s to the power minus 1. K and a have the same units. So if for a second order reaction, k has multiple power minus 1, a would also have the same units. And this is since the first order reaction, units of a are s to the power of minus 1. And the units for rate constant k in Arrhenius equation is first order reaction is always s to the power minus 1. And that's it. Question 5. Hopefully it's correct, and that's 4 marks down the back. Take natural logs. ln k equals ln a minus ea over rt. Rearrange it to get ln a. ln a equals ln k plus ea over rt. ln k, don't make the silly mistake that I did. Substituting k in, it's ln, the calculator, then the k value 3.46 times by 10 to the power minus 8. Minus ea, well, activation energy needs to be in joules because gas constants in joules, you can't have one in kilojoules, another one in joules. To convert that into joules, times by 1000. Divided by R, 8.31, times by temperature. Temperature needs to be in Kelvin, so add 273, so you get 298 Kelvin. You get ln A equals this number. Then we want to find A. We don't want natural logs of A. We don't want ln A, we want A. So we therefore we do A equals e to the power of that. Use the E thing on your calculator, so e to the power of this number, and you get A equals a ridiculously large number, and then the standard form is 2.57 times by 10 to the power of 9. And then the units, since it's a first order reaction and A is going to have the same units as K, the units is going to be s to the power minus 1, and 2.57 times by 10 to the power minus 9 is what A is. And that's the end of question 5.